to talk about full-scale wind tunnel investigations of our MAV, which is a tilt wing. First, I'm going to introduce our MAV. As I already said, it's a tilt wing. We're going to take a look at the special characteristics of such an aircraft, and we will see why we need such a detailed investigation. Secondly, I'm going to present the wind tunnel setup and the measurement approach, and at last, I'm going to evaluate the results. We are participating at the IMAV since 2011 as Team Mavericks, and due to the various mission challenges, we decided to design our aircraft as a tilt wing. This allows us to have stationary flight in a wide range of different velocities. The propulsion system is fixed to the wing, and so the ailerons stay constantly in the slipstream of the propeller, which gives us more control. The tilt wing itself can be seen as a combination of two different concepts of aircraft. On one hand, we have the fixed wing, where the lift is generated by the wing. And on the other side, we can tilt our wing up to 90 degrees and for VTOL and hover, and there the propulsion system produces the lift. The MAV itself is equipped with an additional tail rotor, so we can control the pitching moment in hover. So let's take a look at the interesting flight mechanics of a tilt wing. With respect to the horizontal velocity, the flight envelope of a tilt wing can be divided into three regions. On one hand, we have the pure aerodynamic flight with well-known flight dynamics. The aileron induces a rolling moment, the elevator induces a pitching moment, and for us, the differential thrust induces a yawing moment. On the other hand, we have the hover configuration, where the flight mechanics are pretty similar to a multicopter, but for example, our yawing moment is induced by the ailerons in the slipstream. The third reason is the transition, and we can see the equations for the transition here. And we can see that the transition covers actually all the flight stays in between from hover to a fixed wing flight. Depending on the tilt angle, which is here represented by the tilt angle sigma, we can see that we induce a combination of rolling and yawing moment. So the ailerons, which is represented by delta CA, and here as well, and the differential thrust, which is delta T main, always produces a combination of both moments depending on the tilt angle. Additionally, not only the direction is changing, but also the magnitude of both actuator effects is dependent on the current transition state, as it's dependent on the tilt angle and the dynamic pressure. So it can be stated that the lateral motion, the lateral movement is pretty much heavily coupled, and additionally we have some nonlinear effects like stall that cause instabilities too. And because of all these effects, the transition is often performed as a continuous process. This means we take up in hover, and then right off we go through it, and then we be in fixed wing flight. But actually the advantage of a tilt wing, which means the wide continuous horizontal velocity range, can only be used by satisfying stationary flight states in all these different horizontal velocities. So the presented variances and couplings during the transition shows that we need to investigate the flight mechanics of a tilt wing in wind tunnel measurements, as the equations are not satisfying our needs. At first, we are investigating the required settings of the actuators of the longitudinal motion to reach stationary flight during the operating points in different horizontal velocities. And secondly, in these operating points, the actuators are varied, so we can record the effects in the direction and magnitude. So the wind tunnel of the Institute of Flight System Dynamics is equipped with an open measurement area of approximately 1.5 meter diameter. So with our small size of the MAV, we were able to perform full-scale and full airworthy measurements inside of the wind tunnel. So pretty much we had simulated flight in the wind tunnel. The free stream velocity therefore correlates to the forward velocity of the MAV, and the free stream velocity is varied from approximately 0 to 17 meters per second. The MAV itself is fixed to a weighing scale, which is recording the resulting forces and moments in the center of gravity, and we are holding the pitch angle of the MAV to constant 0, which means that the fuselage, our MAV, is always in a horizontal position. So for example, for any payload or cameras or something like that can always face down. As mentioned, the measurement is divided in two parts. At first, we have the investigation of the operating points of this tilt wing, and on the other hand, we have the investigation of the actuator effectiveness in these operation points. So for each of the two investigations, I'm going to present the measurement approach first, and then I'm going right away to the results of this measurement. The operating points are investigated in horizontal velocities in steps of 1 meter per second steps. And they are reached by manual variation of the three actuators: tilt angle, thrust, and the elevator or tail rotor deflection. And for stationary flight state, we need to have these equations, the equations of longitudinal motion, in equilibrium. This means the x, z, and m force m moment have to be 0. But we are only investigating longitudinal motion as we assume the lateral motion in a constant equilibrium due to the symmetry of the MAV. The weighing scale itself is calibrated without the MAV mounted on the weighing scale. So at this moment, we have here a plot of the measurement of 13 meters per second. So in the beginning of the measurement, we have about 16 newtons weight of the MAV. And we produce about 6 newtons drag in the negative x direction. And we have to vary the tilt angle and the thrust to reach an equilibrium point of 0 and 0. And in the end, we also have to deflect the tail actuation to also reduce the pitching moments to achieve a stationary flight state, also a trimmed situation. Now let's take a look at the different trim values we found out. So the three actuators, as mentioned, are investigated, and all the following measurement plots we are now talking about are equipped with a compensating function of different orders. This means we use them as a trade-off between good smoothing and, on the other hand, good reproduction of the measurement points. We can see that not the whole range of the tilt angle, which goes from 0 to 90 degrees, of course, is used. This is because a tilt angle of 90 degrees would produce a negative x force due to the propeller-induced lift of the wing. So for hover, we need a tilt angle of approximately 85 degrees. The tilt angle represents both the direction of the thrust and the direction of the lift of the wing. So the tilt angle decreases with an increase of the horizontal velocity as the lift of the wing increases quadratically. Now here we can see the thrust given in terms of rotational speed of the main propellers. And thrust is used to compensate the gravitational force in hover, of course. And so it decreases with an increasing lift force of the wing. On the other hand, in the fixed wing mode, the thrust is necessary to compensate the drag of the MAV. And therefore, we have a minimum required thrust at about 12 meters per second with an increase of the drag at higher velocities due to the increasing drag. The necessary elevator and tail rotor deflection can be seen here. And due to the low effectiveness of the elevator at low velocities and hover, we are using the pitch of the tail rotor deflection to compensate the pitching moment. And in velocities from 0 to approximately 10 meters per second, we use they both actuators in combination. At a horizontal velocity of 10 meters per second, the elevator deflection is effective enough to compensate the pitching moment, including a provision deflection for pitch control, of course. At this point, the tail rotor is not necessary anymore and can be turned off. At last, so for constant conditions during these measurements, the MAV is powered from a power adapter, and therefore the power consumption itself can be analyzed as well during these measurement points. And the MAV propulsion system, the main propulsion system represents the main power consumer, as the plot is pretty similar. But at the point we turn off the tail rotor, we cause a drop in the trend, of course, and therefore the plot has to be splitted. The most efficient and therefore longest endurance flight can be accomplished at 12 meters per second. So we can sum it up. It is possible to associate deflections of all the actuators of the longitudinal motion to points in horizontal velocity. And as these relationships show no discontinuities, and they can be used for a feed-forward controller. And now let's take a look at the actuator effectiveness in these operating points. Therefore, all actuators of the MAV have been deflected, but in terms of time, I'm only going to present the ones which are interesting for the attitude controller. So in these already presented operating points, a MATLAB script commands actuator deflections as here shown. And these MATLAB scripts run on our flight computer, which has been developed in the Institute on Flight Systemic Dynamics, and it's called FLUCO, which is shortened German for flight computer. You can see the trim deflections of the elevator, the tail rotor, and the thrust as offsets from 0 here at this point. And the deflection is set for 25 seconds, followed by a 10-second pause. And this is as the averaging of the weighing scale is pretty slow, and so we only investigate the stationary effects, and no actuator dynamics are taken into account. Every actuator is deflected as follows. On one hand, we deflected them positive and negative to see if the actuator effect can be seen as symmetric. And on the other hand, we deflected them in a small and in a big range to check if we can see them as a linear effect, and therefore we could extrapolate them. The following are now going to presented actuator effects are all be seen as symmetric and linear. Here you can see the effects of a positive normalized deflection of the differential thrust actuation in rolling and yawing moment. And the trim points here are given with respect to the tilt angle, and here we can see we have the hover case on the left side and the fixed wing with 0 degrees on the right side. Looking at the rolling and yawing moments is a vector. We can say that they rotate with the tilt angle, of course. And this effect also improves the equations we saw before. And I plotted these two equations in dashed lines here. And I scaled them to the uninferred inflow of the main propulsion system in hover. And therefore, we see that we have great deviations between these two. And they might be caused because the inflow of the propellers, of course, changes with higher inflow velocities. And so the main impact can be seen here in yawing, where we have reduced the possible yawing moment in fixed wing flight to approximately 6 Newton meters. So we can sum it up that the change of the direction of the actuator effect is because of the rotation of the wing, and the change of the magnitude of the actuator effect is because of the change of the inflow. Here we can see the effects of a positive normalized aileron deflection on rolling and yawing moments. They are pretty similar to the differential thrust, as they show a change in direction and magnitude. The change of the direction, of course, again can be put to the rotation of the wing, but the magnitude is as predicted in the equation 1 and 2, which are presented in dashed lines again, dependent on the dynamic pressure. And the dynamic pressure is influenced by the free stream velocity, of course, and on the other hand, by the slipstream of the propellers again. And so we can see that in hover, the dynamic pressure only consists of the slipstream of the propellers, and therefore we only can produce a pretty low yawing moment. And on the other hand, in fixed wing flight, where we have like 17 meters per second free stream velocity plus the slipstream of the propellers, we can produce up to 3 Newton meters of rolling moment. The effects of the elevator and tilt rotor pitch deflection in pitching moment are presented here, and as the tilt angle is not the main influence for these actuators, we put it again to the horizontal velocity of the MAV. So the effect of the elevator is pretty much quadratic to the horizontal velocity, and therefore the plot shows a pretty expected trend. But the effects of the tail rotor deflection is caused by many different influences, as the inflow, the tilt angle, the slipstream, and so on. And in total, we can see that the influences cause a increase of the effect with an increasing horizontal velocity. So we can sum it up that the measured actuator effectiveness will help us to decouple the steering of the tilt wing, and an inversion of these actuator effectiveness might help to have an unification of the flight characteristics of this airplane over the whole flight envelope of different velocities. And for evaluation purposes, we performed a second wind tunnel measurement with an identical setup, only that the MAV was connected to the weighing scale by a ball joint now. This means it's allowing rotational movements around the center of gravity, but the forces are still recorded by the weighing scale. During this measurement, the actuators of the longitudinal motion are controlled by, steered by the Fluco. Therefore, the controller was designed in MATLAB Simulink, which can be seen here. And the lookup tables we can see here are dependent on the horizontal velocity. And so the feed-forward controller is based on the compensating functions we were discussing right before. And they are discretized in steps of 0.5 meters per second and therefore linearly interpolated. For horizontal velocities from 0 to 10 meters per second, the remaining forces in x and that direction were recorded by the weighing scale. The measurement setup can be seen here, and the ball joint is visible here. And we can see that the remaining forces around 0 are just varying in a small range in x and that direction. And these would cause in small accelerations during real flight. So we can sum it up that by the wind tunnel measurements, we gained great insight in the difficult flight mechanics of a tiltwing MAV. And based on these measurements, we were able to design a feed-forward controller that is allowed to stationary trimmed flight in the whole flight envelope of the MAV. The controller now is able to balance the forces and moments at any commanded horizontal velocity. And for pure aerodynamic flight, we also proved the concept in free flight higher than 10 meters per second I just presented. The change of the effects in actuator of the actuators in direction and magnitude have been recorded and analyzed. And an inversion of these effects helped to design an attitude controller that is pretty much decoupled in rolling and yawing. And we proved this yesterday at the flight competition. Thank you very much. Are there any questions? Yes, please.
You do have a pitot-static tube on the aircraft.
Yes.
To determine the airspeed.
Yes, the question is about the pitot tube we have installed on aircraft. Yes, we do have one at the moment. During the measurements, we didn't have one, so we always commanded the velocity that was in the wind tunnel. So we were not controlling the velocity, but now we are able to control it, not only feed forward, but also feedback. Was that okay? Yes?
Was your wing cambered, and can you relate what approximately your disc loading was in the cover for your tail wing?
My what?
Was the wing cambered?
Yes.
So it was cambered?
Yes.
Okay. And the disc loading, I don't know if you're familiar with the term, how much thrust per area of the rotor?
Yes.
Do you know what that value would be?
No, sorry, I don't really know. Thank you. Any more questions?
Yeah. We have plenty of time for questions. Anyone? Okay, I may have one question.
Yes.
I believe you two rotors are contra-rotary to equilibrate the
Yes.
differential moments. And so when you are hovering, you are using the differential thrust to control the yaw, the roll,
yes.
mainly. But then it should also produce a yaw.
Of course, because they are different.
And did you see these effects in your measurements when you were trying a differential with the wing completely tilted up?
Probably we saw them. We didn't really put our focus on them. We just inverted it, and then we were fine with that. But we only investigated stationary effects, and therefore usually in real flight we have a pretty huge tail, so maybe this would not affect so much, but in stationary effects we should have recorded it, yes.
Okay, so that's negligible against the
yes.
roll. Okay.
Right.
Any more questions?
Yes, please.
Yeah.
Also, a question on the two propellers.
Yes.
They are counter-rotating.
Yes.
And are they rotating in the direction of the tip vortex or against it? And did you do tests to if that was an improvement or not?
Maybe he can help me out.
Wait. Maybe can you repeat your question?
Yes.
No, oh, okay.
My question was, you have two counter-rotating propellers, and rather on the outboard of the wing, and they interact with the tip vortex, of course, and you
Yes.
can make them turn so that they counteract the tip vortex, which could decrease drag,
Yes.
or go with the tip vortex.
Okay.
Did you do tests on that?
An answer from the public.
Maybe it might help. The white propeller is running clockwise, but the white propeller is running clockwise, and we didn't change that during wind tunnel tests. But so it's against the vortex.
Right.
Is that
But
clockwise looking at the aircraft?
Looking as pilot,
Okay.
Yes.
so in direction
Right.
of flight.
but we did not really investigate the different settings. Okay. Any more questions? Yes.
Have you thought about using variable pitch propellers and see how that would improve
What kind of pitch?
variable pitch?
On the main propellers?
Yes.
No, we did actually not do that because we already have huge problems with variable pitch and on a propeller on our tail. So we are already trying to get rid of that, and we don't want to have more mechanical problems on the main propellers. But yeah, that might be interesting for pitch control, of course, yes.
Any more questions? Okay, so thank you very much.
Thank you.